Hello everyone, my name is Darsh Gandhi. I am from CSP IT. My roll number is 24IT0202. Today I am representing about digital maze game using combinational logic. Discover how interactive entertainment meets logic gate design. This presentation shows a digital maze game powered by combinational logic. Introduction to digital maze game. What is digital maze game? A game where player find path to reach a goal digitally. Logic gates validate paths simulating decisions. Using logic gates. Logic gates check if the player's path is valid. Each step corresponds to the gate output, enabling or blocking progress. Motivation behind the project. Educational value. Visualizing logic gate function through gameplay enhanced learning. Logic gate design practice. Construct practice understanding of combinational logic circuits. Entertainment meets technology. Fun way to showcase digital circuit application in the game. Defining the core challenge. There are many challenges for making the game. Challenge validate player path correctness using only combinational logic. Constraints. No memory elements or feedback loops allowed in design. Verification. Outputs must confirm the exact correct path. Now, we will see about project objective. Build the maze, create a digital grid representing maze pathways, implement logic using combinational logic gates to verify validity. Logic gates such as NOR, and etc. Game functionality. Player inputs a path, system validates correctness instantly. Now, how to design a maze game? Maze design overview. Grid layout. The maze is a grid of cells connected through paths. Paths encoding. Paths encoded as binary signals indicating open or blocked routes. Player path representation. Input mechanism. Player use switches or buttons to select the path. Binary encoding. Player choices converted into binary inputs for the logic circuits. Basics of combinational logic. Key gates. Mainly gate use the AND or NOT XOR and NOR gates for the basic of logic. Functionality. Each gate performs specific logical operation on inputs. No memory. Outputs depends on only on current inputs, no historical data. Now we will see about combinational versus sequential logic. Combinational logic, no memory elements in sequential logic, uses memories or feedback loops. Output depends slowly on inputs in combinational logic. Dependent outputs in sequential logic. Simpler, faster responses in combinational logic. More complex design in sequential logic. This is the difference between combinational logic and sequential logic. Path validation logic concept. Gate network. Logic gates combine clear inputs to form validation signals. Match check. Output becomes true only if path matches the predefined correct route. Instant feedback. Game immediately shows if chosen path is valid or not. Truth table example for path validation. This is basically the truth table in which input path are 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Path valid. No, yes, no, yes. Output signal 0, 1, 0, 1. Logic expression for the path validation. Boolean expressions define the condition for the correct maze path. These expressions use AND, OR, and NOT gates to combine inputs. The logic outputs true only when the player's path matches the solution. Now we will see the logical circuit diagram. This diagram illustrates the gate level design for validating maze paths and or and NOT gates combine clear inputs to confirm correct routes. The correct circuit outputs a high signal when the player's path matches the solution. This is basically the circuit diagram in which AND, OR, and NOT gate are used. Implementation approach. Hardware setup. Use breadboards and ICs to build the logic circuit physically. Software simulation. Tools like Logisim and or Multisim simulate the gate logic digitally. Testing and debugging. Validate circuits and pathways step by step for accuracy. Comparison. Hardware offers hand-on learning. Simulation allows easy modifications. User interaction in the digital maze game. Input mechanism. Players select path using switches or buttons aligned with maze rules. Feedback system. LEDs indicate valid or blocked path instantly for the player guidance. Additional alerts. Buzzers provide audio cues to enhance the interactive experience. User's experience. Immediate visual and audio feedback improves engagement and decision making. Design challenges in digital maze logic. Signal interference, noise and glitches cause occasional false outputs. Logic complexity, managing multiple paths, increase gate levels and delay. Error detection, identifying incorrect paths require careful Boolean expression design. Hardware limitations, breadboard connection introduce unexpected signal drops. Debugging, tracing errors was time consuming without automated tools. Advantages of this approach. Simple implementation, easy to build and understand using basic logic gates. Fast validation, immediate feedback on paths correctness enhances gameplay. Educational value teaches fundamentals of combinational logic and Boolean algebra. These are advantages of the maze game. Future enhancement. Memory elements incorporate flip-flop to remember play, progress, and choices. Timers add countdowns to increase challenges and urgency during play. Multiple levels. Design progressive difficulty with varied maze complexity. Adaptive difficulty. Adjust maze challenge dynamically based on a player's skill. Conclusion. We explored digital maze game logic using combinational circuit. Key lessons include logic design, debugging, and interactive feedback system. Future work focuses on memory, elements, and adaptive difficulty. Please feel free to ask any question or share your thoughts. So this is how we made the maze game using the combinational logic. So that's all for it today. Thank you everyone. Myself, Darsh Gandhi from 24IT020. Thank you.